Hi roboticist! In this series of video we are gonna talk about ROS Control, and in fact what we're gonna do is to create a custom controller for each joint of the cobot that we have built so far. And I remember you that it is a 6-axis robot, so what we need to do is to create for each joint a controller in such a way that we have the instrument that allows us to make the robots what we want to do. Before diving into it, make sure to subscribe to the channel, turn on the bell for notification when another video pop up. So now let's get into it. If you remember from the last video, we have created and we have modeled our cobot that is an expression of URDF file, or better, it is modeled in a URDF file, and we have created our chakra file where we have modeled the link for a cylinder, a box, and the joint in such a way that for each link and joint we do not need to repeat every time, so it is a manner that allows us to simplify our robots. Then what we have done is to create a launch file that allows us to spawn the robots that we have modeled, and we have spawned in an empty world, and we have decided to spawn the robot in the position 0, 0, 0 of our empty world environment. Then I'm gonna refresh you what happens if we spawn the robot and we press play without any control. So let's try it by typing ROS launch, cobot simulation, which is gonna be the name of our package, and then the spawn robot launch. Okay, here we go. You can see that the cobot it is in a straight position where every joint is in a 0, 0, 0 regions position, and if we press play, the robot falls down. Why that? Well, as I already mentioned, we don't have any control in each joint. This meaning that when you press play, the robot feels the gravity of the environment and everything falls down. So this is the scope of this series of video. What we need to do is to create a ROS control, and before diving into it, I want to make a list of all the activities that we are gonna cover in such a way that we have a good track of what we are doing. So here we go. This is a list of what we need to do for creating a ROS control for any kind of robot that we wanna model. So first you need to create a transmission for each joint. Then you're gonna need a Gazebo plugin that helps you to interact your ROS package with Gazebo, because you need to make them talk to each other. Then you're gonna create a YAM file for every joint in order to control, which is imagine that is configuration file that describes which kind of controller you want to put in each joint. Then you need to create a launch file to spawn not only your robots that you have modeled, but also the configuration of your joints. And in the configuration file we're gonna put a PID control that are not tuned. So the last step that we need to do is to tune the PID control, which stands for proportional, integer and derivative control for each joint, and we're gonna use RQT reconfigure GUI for tweaking those values. Okay, now you should have a good understanding of what will be our pathway to create our first ROS control. Then we're gonna start with the transmission. Before to create our transmission tag for each joint, what we need to do is to add some dependencies that are needed for our ROS control package. So what we need to do is to add to the SIGMEC list the dependencies controller manager, joint state controller and the robot state controller. And as you imagine, you have to add the same dependencies in your package file. So we need to create your build depends, the build export depends and exec depend for the dependencies that I already talked to you. Okay, after this introduction, we can start to create our transmission tag. And as a good approach, we are not going to create our transmission tag in our URDF file. This is because we will need to create a transmission tag for each joint. And it's gonna create URDF file too much complex. So we are gonna use the same approach that we did in the last video for the links and the joints. So we're gonna create a chakra macro tag, and this will be a transmission macro, and we need to pass to these macros these parameters, the name, the joint name that we have already assigned, and the actuator name. Okay, now inside the chakra macro tag we need to actually create our transmission. So we need to pass it a name, and this name will be assigned in the URDF file. And this transmission is characterized, let's say, from a type that is going to be a transmission interface, which is a simple transmission. And then we need to tell to the transmission what will be the joint that will have this type of a simple transmission. So we need the joint name that we need to assign to the URDF file. Then we need a hardware interface, and for hardware interface we are going to use the effort joint interface, meaning that we are going to pass to the controller an effort value, and we are gonna convert it in a position, but it's something that we will cover afterwards. And last, we need to assign to the transmission the actuator. So we need an actuator name, and this value will be passed to the URDF file as well. And in this actuator, that often will be a motor, just to make you understand, it will have a hardware interface as well, like before, and will be the same effort joint interface. So imagine that in the reality we are gonna pass effort values to the motor. Okay, and then we need to select a mechanical reduction that for the moment we could keep 1. Okay, that's everything that we need to have for our transmission tag, or better, our transmission macro, and we need to create, or better, to add to each joint a transmission. So this is because you can have the best controller that you may have, but if you have anything to transmit your value to the motor itself, the ROS controller will be useless. So what we need to do is to put the transmission in each joint. And we are gonna use the same approach as we did for the joint and link. So we need to type chakra, semicolon, then transmission, and then we need to put as a value the parameters that we have selected in our chakra file. So it's gonna be the name, the joint name, and the actuator name. So as an example, the name will be the trans, we can call it trans base link underscore link 1, which is the transmission name of the joint base link link 1, and we're gonna call this actuator name motor base link link 1, which we can imagine that it will be our motor that is gonna be installed in between the base link and the link 1. So it's the motor that is responsible to make a revolute rotation of the link 1 along the longitudinal axis of the base link. And we are going to do the same for the link 1, link 2. And so we put as a name trans link 1, link 2, that is referring to the joint name link 1 and link 2, and the actuator name will be motor link 1, link 2. Okay, I hope that you got the point. And so now we need to make the same for the link 2, link 3, and so on and so forth for all the joints. And we're gonna do the same for the gripper as well. So we need to create a transmission tag for the TCP connector gripper right as well as the TCP connector gripper left. And we need to do the same thing for the gripper as well, even if the TCP connector gripper right and gripper left is gonna be a prismatic. Why that? Well, because it will be in any case a motor, even if it's sliding along one link instead of make a revolution between each other, but the concept is gonna be the same. Okay, we have well created our transmission for each joint. And then what we need to do is to create our Gazebo plugin. Why that? Because as I said to you, we need a tool, or better, a plugin that allows the ROS, or better, the ROS control, to communicate with the Gazebo, which is another type of software, which is a physics software. So we need to create a tag, Gazebo, and then put the plugin tag the name of this plugin, which is gonna be Gazebo ROS Control, and then the file name. This file name is very important because it will do all the dirty works for us. So you will see later on that when this plugin will be spawned in our model, this plugin will take all our joint transmission whatever, and it will create the topics needed to control each joint for us. And this is very important because without that we will not be able to control our joint, simply because all the joints and all the transmission cannot talk to Gazebo, which is our environment. And another important thing is to create a robot namespace. In our case, we're gonna call it cobot. This is very important because we might have a different plugin for different robots. Imagine that we are gonna create a simulation with different robots, and we need to assign to each robot a Gazebo plugin. Okay, now our Gazebo plugin is done. During the checking, I need to point out some dummy errors that I made, so make sure to do not fall in the same error. Okay, so we can spawn the robots in our Gazebo environment to check if everything works as before. So we launch the file. Okay, this is imposed. Then if we press play, the robot should fall down again. Okay, this is falling down even if we have our Gazebo plugin and the transmission, because now we have all the tools needed for creating actually our control for each joint. Now we are, let's say, at half of our pathway for building our ROS control for our 6-axis robot model in URDF. We have created our transmission tag for each joint and we have put our Gazebo plugin. Now we have everything we need to create our configuration file where we are gonna put our controllers. And since that it is a quite complex robot with 6 joints and more than 6 links, I think that it is a good practice to simplify as much as possible our model in such a way that we can focus on the joint controllers and its parameter to tune, which will be, you will see in a moment, the PID values. So what we're gonna do is to comment out all the link that we don't need. So we're gonna comment out the links from the links 3 on, as well as the joint from the link 2 and link 3 on. So after this simplification, what we're gonna have is the base link, the link 1 and the link 2. And the joint that we're gonna have is the joint base link 1, which is responsible for the revolution of the link 1 along the longitudinal axis of the base link, and then the link 1 link 2 joint, which is responsible of the revolution of the link 2 along the edge of the link 1. Okay, we have simplified our model, and let's spawn these new robots in the environment, and we can see now that we have only 3 links: the base link, the link 1 and the link 2, as well as the 2 joints, base link 1 and link 1 link 2. If we press play, we're gonna see that the link 2 is going to fall down. This is the same behavior that we have seen so far with all the joints of our robots. Okay, so if you think nothing changed from the last view, so now we can start to make the configuration of these 2 joints. I remember you, the joints that we are going to configure are base link 1 and link 1 link 2. So in the config folder we are gonna create a new file and we're gonna call it joints underscore controllers.yum. Okay, here we go. First of all, we're gonna put the namespace of our robot, which is cobot. This is because we are gonna set all the joints controllers to the cobot robots. And everything that I'm going to code from now on are referring to the cobot robot, or better, the cobot namespace. So first we need to publish all the joint states. So we need the joint state controller, semicolon, and then the type of this joint state controller is gonna be joint state controller. If you remember at the beginning of this tutorial, this is the dependencies that I wanted you to add to your CMake list and the package file. And for this we're gonna set up a publish rate of 50. Then we need to make the position controller and set up our PID. So we can call the first controller joint 1 position controller. The type is gonna be effort controllers joint position controller. So if we set a type of a controller of a certain joint, effort controller slash joint position controller, this convention meaning that we are going to pass as an input from the software a joint position, and then the software will translate this position into an effort controller. So the motors that we're gonna have as an hardware will receive an effort input. So the software will take as input the joint position controller and will give to the output an effort values that will be passed to our hardware, or better, our motor that will be in that joint. And the joint that we are gonna put in the joint 1 position controller is the first one, that is gonna be the base link underscore underscore link 1 that we have already modeled, and we have our transmission tag for this joint. And last, we need to put our PID value, which I remember you that stands for proportional, integer, and derivatives. We are gonna put first guess value as proportional 700, integer 50, and derivatives 70. This value will be tuned during our simulation thanks to our AQT reconfigure package, but this is something that we will talk afterwards. So what we're gonna do now is to make the joint to position controller as we did before. So we just change the name of the joint, which of course will be link 1, link 2, and then for the moment we just keep the same values of the proportional integer and derivatives values. And we're gonna keep the same type of controller. That is gonna be a foor controller joint position controller. And now we have set up, or better, we have configured our first two links, and we have add, of course, the joint state publisher. So what we're gonna do now is to create our launch file that spawn not only our robots but all the configuration of each joint. So we need to pass as a parameter of this package our YOM file, which is something that we're gonna do in the next video, where we're gonna deal with the launch file. Hi roboticist! In this video we hand over from the last video where we have created the configuration file in YOM format for the controllers of our robot with the simplified design that, I remember you, is gonna be made by 3 links and 2 joints. In fact, in our configuration file we have set up the joint state controller that it is necessary to track the state, like position of each joint over the time, and then we have configured the controller giving to them the following setup: the name, the type, the joint and the PID values. The name is arbitrary, and in this case we have chosen, for example, joint 1 position controller, and for the type effort controller / joint position controller. And this convention means that we are going to control the joint giving a position. And then the ROS controller package will translate the values in effort data that will be transmitted to the hardware that will be a motor. The joint we need to keep the name that we have set up in the URDF file, and finally we have given PID values a first guess. These values will be tuned in the next video, and I will show you how to do that. So we can now create a launch file that spawns the cobot in Gazebo with the controller configuration. We can update the spawn robot.launch file, adding the controllers. And for keeping things separately, let's make another launch file and name it spawn robot w controller.launch. So copy and paste, and now we need to add the controller configuration, and we can do it by passing as ROS parameter the YOM file that we have just created. Then we need to load the node controller manager, for which we have already set up our package with these dependencies. The controller manager belongs to the controller manager package, and the executable file is called spawner. So you can set the output as a screen, respawn as a false, and assign as a namespace cobot.
Finally, as arguments, we need to put the joint state controller necessary for the joint state topic for each joint, and then the name of the controller that we have decided in the YOM file, that is gonna be joint 1 position controller and the joint 2 position controller. We have our namespace that is gonna be cobot, and so we need to remap the joint state topic belonging to the node robot state publisher with the namespace cobot joint state. This is very important because if we don't do that, the robot state publisher package is not allowed to create the joint state topic with the right namespace, and we won't be able to control our robot. Okay, we are done and we can launch the simulation, and we can see the robot simplified with 3 links and 2 joints, and let's check what happens when we press play. You can see that the robot keeps straight, but it is acting very weird. Why that? I wanted to show you this problem that might happen when you model your robot and you spawn in Gazebo, so you will be able to overcome this issue. What is happening is that the robot is floating in the environment, so we don't have any, let's say, binding reaction to the robot control. So in order to do that, we just need to create a fake link that represents the world and a fixed joint that links the world to the base link. So let's do it by modifying the URDF file. At the very beginning, create a link and call it world. And right after, let's create a joint of type fixed that links as parent the world link that you have just created, and as a child the base link that you have modeled in the URDF file previously. As you can see, we don't need to specify anything because it is only used for fixing the robot somewhere. In this case, it doesn't matter where, because we are spawning our robot in an empty world. And of course, if we will need to define, we will need to define the position if we want to spawn the robot in a specific world. So let's launch it again. And now you can see that the robot stays straight and it is fixed in the world. This means that the controllers are corrected set up to the 2 joints. Let's check the topics that are working right now. So by typing ROS topic list, and you can see that we have a lot referring to the joint position controller and joint states and so on and so forth. But if you think we didn't create in our package any node and topic either like that with that name, so what is the tool that is providing all this topic? Well, the tool is the Gazebo plugin that we have put in our URDF file at the end, that is calling the library that takes care of creating a connection and communication between the controller manager and the joint configuration with the Gazebo environment. We have everything now to test the robots, control it by publishing a joint position for a specific joint. We can do it via command line by typing ROS topic pub -1, meaning that we want to publish only one time, to the topic cobot/joint2position controller commands. Then type tab for auto compilation, and we can see the type of the message that you can publish, and finally the data. The data that you are gonna put is the angle in radians of the joint that you want to be at. As a first guess, we can put 1.557, so it's gonna be 90 degrees, and you can see that it's going to 90 degrees. Let's do it again, but this time minus 1.57, and you can see that the link 2, or better the joint link 1, link 2, is going to the setup position. Let's change the joint, and feel free to get familiar with these commands, and you can play with any degrees that you want to test. That's all for today. We have created our launch file to spawn the robot and its controller manager, and we have tested the behavior of each joint when we are publishing a joint position in radians. I hope that you enjoyed this video. If yes, please subscribe to the channel and turn on the notification bell to do not miss the next topic, where we will learn how to tune the joint controller in PID value, that I remember you for now are only guess values, with the help of the very useful tool provided by ROS, that is gonna be RQT Reconfigure. After that, we will complete the model of our robot, and we will be ready to play with the pick and place manipulation. And I'm looking forward to show you that. Thank you for your attention, and keep learning robotics with ROS.
Hi roboticist! In this section of ROS Controller, we will see how to publish the joint position controller command using the package RQT package. And in the last video I remember you that we have done it via command line. In ROS exists a very user-friendly GUI that you can use in your simulation, and allows you to test very easily how each joint behaves to a certain command in joint position. So if you want to add this GUI in your simulation, you can just simply add a node in your launch file. So let's do it. And before the end of the launch tag, you can open brackets and add a node, and we can call it RQT Reconfigure, and then the package is gonna be RQT GUI, and has the same name for executable file in type RQT GUI. So then we can launch this launch file and see what happened. And And as you can see, the robot is spawned correctly in our environment with a simplified version, let's say, with only three links. Then if we press play, the robot stands, so meaning that the ROS controller is working. And then let's open the GUI, and if you click refresh, the refresh button, you can see at the section, at the window of topic, all the topics that are available. And all these topics are automatically generated thanks to the Gazebo plugin. So you can see that when you click the topic, the type is going to be fulfilled automatically, and you can see that the type of this topic is going to be standard messages / float 64. And then on the right you can choose the frequency that you want your topic to be published. And if you press the bottom plus in green, you can see at the main window that the topic is going to pop up. You can see that there is the rate of 100, and if you press the arrow, there will be the data that you can publish. So we can set as an expression scalar data, where we can try, for example, 1.57 in radians, that remember is going to be 90 degrees. And then if you tip the window, you can see that the joint that links the link 1 and link 2 is working, and the link 2, you can see that is moving to 90 degrees. Then we can test it again, and in the expression now we can set minus 1.57, and if you type enter, the joint is going to work and is going to put the link 2 at the opposite side. Then you can add another topic. For example, let's do it for joint 1 position controller command. So I remember you that this joint links the base link to the link 1. So the link 1 is going to make a revolution along the longitudinal axis of the base link. And if we set up an expression of let's say 1.57, then click tip the windows, and you can see that the joint 1 position controller is working. Then we can come back to 0, and so on and so forth. So feel free to check all the position and test your simplified robots. So, as you can see, nothing new compared to the position sent via command line. So it's gonna be the same. In the last video we have sent a radiant joint position via command line, and in this video we have sent the same messages via RQT GUI. So now what we need to do is to check if the P values of the controllers for each joint are correct. And how can we do that? Well, usually a good practice to do that is to send to a joint a sinus command between a lower and an upper limits of the joint itself and check what will be the real actual value of the joint. So, as a recap, we will have two values. The values that we ask the joint to be at, which is the command topic, and the second will be the real value that the robot is at that moment in real time, in real life. So this value will be the process value that is monitored in another topic that we are going to see in a moment. So you can imagine that there will be an error between these two values over the time, and the scope is to trick the PID values of the controllers in order to minimize that error. And what we're gonna do is to visualize this error via a plot of these two variables over the time. So let's do it right away. So in the expression side of our joint 2 position controller command, we can send to this joint an expression of the amplitude that is going to be 90 degrees and sinus I/100. So I represents the time frame, 100 is going to be the frequency that we are at, and the 1.57 is the scalar values for the amplitude of this sinus message. So these expressions means that we are continuously publishing a message of type sinus at the frequencies of 100 Hz, and the joints need to oscillate between plus and minus 90 degrees. So if we press enter, we can see that the joint 2 position controller is doing his job by oscillating the link 2 from one side and from another side, or better, from plus 90 degrees and minus 90 degrees. Okay, this is the expression of the command topic of the joint 2 position controller. And now what we want to do is to plot this value. So if you go to plugin and go to plots, so you can see that the value of the joint 2 position controller command is plot in the windows. So go to topic and type cobot / joint position controller command, then click and / data, and you can see the values. Okay, then what we need to do is to compare this plot with the state and the process value that represent the real value that the joint has. So here you go. In light blue you can see the plot of the command data, that is the input that the controller is sending, and in purple you can see the state process value, that is gonna be the real position where the joint 2 is at in that moment. So now what we can do is to check how the proportional integer and derivatives values affect the controller of its joint. So if we go to plugins and looking for a dynamic reconfigure, you can see that if we click to the cobot namespace joint to position controller, in the main window is popping up the three values p, proportional, integers and derivatives that, remember you, in the configuration file has been set up as a first guess. So for example, let's check what happens if we put as a proportional data minus values, and you can see that the process value is going without controller. And if we increase the proportional value, well, the process value is going to reach the data value, meaning that the error can be negligible. And the same thing we can make it with the integer, and you feel free to check the good values, but we can see that if we set proportional value as 700, integer at 50 and the derivative of 70, the error is gonna be negligible. So we can consider these three values good. So I hope that you got the point here, and what we're gonna do in the next video is to tune the PID value for each joint of the robot that we are going to reconstruct from the link 3 on. I hope that you enjoyed this video. If you like this video, don't forget to subscribe to the channel and turn on the notification bell in order to do not miss the next topic, which is gonna be interesting. Thank you for your attention and keep learning robotics with ROS. Hi roboticists! In the last video we have learned how to tune the PID controller for our joint position controller. And we have done it for the joint 1 position controller and joint 2 position controller. And the robot model that we have controlled was made by 3 links: the base link, the link 1 and link 2. So now what we're gonna do is to add another link, so the link 3, and first we are gonna see if this affects the PID values of the previous joint controller. And if it doesn't affect nothing, what we can do is to tune the PID controllers for the joint 3 position controller, that I remember you is the joint responsible for making a revolution of the link 3 along the edges of the link 2. So let's do it right away. The first thing that we need to do is to update our cobot URDF file, and we need to include the link 3 and the joint named link 2 and link 3. Then, since that we add another joint, we need to uncomment the transmission for that joint. That's gonna be link 2, link 3. So we are generating the motor for the link 2 and link 3. Then, of course, we need to update our joints controllers YOM file. So it's gonna be our configuration file for the joint that we want to control, and we can create the joint 3 position controller, and we can keep the type as the same. So for controllers, joint position controller, and of course we need to change the joint name, link 2, link 3. And finally we need to update our launch file, and in particular we need to update the arguments of the controller manager, like I'm doing right now. So everything is ready, we can launch the simulation. And you can see that now the third link, so the link 3, is spawned correctly in the position where we have set in the URDF file. So take a moment for configure better the GUI in such a way that you can see the windows and the simulation as well. As you can see, when you press play in the simulation, the robot stays straight, meaning that all the controllers are correctly set up. But we are going to check it using the method that we have seen in the last video, where we have used a plot to see the behavior of the command topic for each joint with respect of the status process value. So now we need to add to the topic the joint 3 position controller command. And then as an expression, let's start with the 90 degrees, and you can see that is acting correctly. Let's try minus 90 degrees, so minus 1.57 radians. Press enter, and you can see that even if the third link is moving, all the other links, or better the other joints, are not moving anymore. So this means that the moving of the link 3 doesn't affect the joint position of the previous joint, of the previous motor that we have set, the joint 1 position controller and the joint 2 position controller, meaning that the P values that we have set up in the last video are good enough to overcome any misalignment on the position that might happen for inertia when you move only one link and keeping stable the others. What you can see is that when the link 3 is going to the 90 plus 90 degrees, the link 2 is slightly following the direction of the link 3, meaning that probably we are going to add an error between the command and the process value of the joint 2 position controller. But as a first guess here, for tutorial purpose, we can keep just as is. So now what we can do is to check the error between the command data topic and the state process value topic. So in the plot section at the tab of the topic, just type cobot slash the name of the joint that we want to control, that is gonna be the joint 2 position controller that we have set in our configuration file, then slash, then command, and then the data. And this should be at 0. Then add the joint 2 position controller state process value, that is going to be 0, and we can check what happens to this value when the link free is going to plus 90 degrees. We can see that the position of the joint 2 position controller is kept at 0, meaning that the fact that the link free is moving doesn't affect the controller of the joint 2 position controller. So now what we can do is to add the joint 3 position controller command data that is popping up at light blue color, and then plot the state process value. And you can see that these curves, the light blue and the purple one, are overlapped. So meaning that the errors between the command data and the state process value of the joint 3 position controller can be negligible. So this means that the PID values that we have set as a first guess in the YOM file can be considered as good. So now we are gonna make something funny, and we can make the joint 2 position controller oscillate as well in a sinus manner. So but this time with the amplitude of 1 radians. So you can see that the whole robot is rotating along the longitudinal axis of the base link, and you can see that these values are overlapped. So then we are gonna do the same for the joint 2 position controller. So tip the windows, and now you can see from the plot that even the joint 2 position controller, the command data and the state process value are overlapped as well, even if the joint 3 position controller is oscillating as well between plus and minus 90 degrees. So this plot shows you that the PID values set up for the joint 2 position controller and the joint 3 position controller are correctly set, because the moving of one doesn't affect the precision of the other, and vice versa. So we can challenge the PID values. So open the dynamic reconfigure window, and we can put the proportional value to 1000. And we can see that this changement doesn't affect the errors between the command data and the state process value. So meaning that the joint free controller is reliable. So what we can do now is to change the velocity of the joint free position controller, and you can see that when you press enter, the command data topics is changing like it is a step, the values, and the process value with a certain delay will follow that command. So of course it's very difficult that the process value follows 100% the command data if we introduce a step as a disturb. But we can consider that the errors goes into zero, meaning that the two curves are overlapped again in a few milliseconds. And what we can do is to increase the speed of the joint 2 position controller as well, and see what's happened. You can see that even now there is a step, but the curves are overlapped again in a few milliseconds. So meaning that we have made a good choice in the PID values. So what you can do is also to challenge the values of the PID by introducing a lot of disturb in the command data of the joint that you want to control. So for example, if we increase again the speed of the joint free position controller, and but we can put the derivatives values of 100, so is increasing, you can see that the process values follows the command data, and it reach the target value in a few milliseconds as well. So the key takeaway from this video is that when you add a link to your model, is always important to check the PID values of the joint that you have modeled before, in such a way that the second joint that you have introduced doesn't affect the quality of the controller of the previous joint, and vice versa. And that's all for today. And if you like this video, subscribe to the channel and turn on the notification bell in order to do not miss the next video, where we are going to complete our robots. Thanks for your attention and keep learning robotics with ROS. Hi roboticist! In this video we are handing over from the last time and we are going to add the link foor to our robots. So first of all, let's go to the URDF file and uncomment the link foor and the joint that attach the link foor to the edge of the link 3 that is named link 3 _ link foor. And then you need to uncomment the transmission tag for the joint named transmission link 3 link foor, and then we have finished our update in the URDF file, and we need to update our joint controllers configuration file. And so copy and paste, name the new joint joint foor position controllers, keep the type as F4 controllers joint position controller as well, and of course change the joint name, so link 3 link 4, and last you just need to update the arguments of your controller manager nodes. So all the updates that we needed to do are done, so we can launch this launch file, and we're gonna see that the link foor will appear at the edge of the link 3, just as we have modeled in the URDF file. So as you can see, the link foor is correctly spawned in our cobots, and if you press play, nothing falls, meaning that the default values of the PID that we have put are okay. So refresh the topic, and we are going to looking for the joint foor position controller, because we want to send a joint position command as we did for the last joints. So select the joint foor position controller command, set the frequency at 100 Hz, and put 1.57, that is gonna be 90 degrees, and tip the windows and see what's happened. And you can see that is going, the link foor is going to 90 degrees, which is okay. Then we can try to send a position controller to minus 90 degrees, and is responding well. So now, as we did for the others joint, we can send a sinus expression to the joint foor with the amplitude of 90 degrees. So as you can see now, the joint foor is oscillating between plus and minus 90 degrees. So what we can do now is to add to our plot the joint for position controller a command topic and compare to the state process value to see if there's any misalignment or it's well overlapped. So we are adding now the command data topic. And now we can add the state process value topic of this joint. And see how this joint behaves to the input of the position controller. And you can see that there is a good overlapping, meaning that we don't have any important errors between the input that you are sending to the joint and the actual values of the joint itself. And what we can try now is to increase the velocity of the position command. And if we set 4, we always have this step disturb. But as you can see, there is the state process value that try to reach the command data, and in particular when we are approaching the 90 and minus 90 degrees, there is a good overlapping, so the error is 0, let's say. But when we are approaching the middle, let's say the 0 degrees, there is a mismatching between the data and the process value. So we are going to try to solve this problem by tuning the PID values. So let's try by increasing the integer value from 50 to 70 and see what happens. It seems that the situation is improved. Let's try 80. Okay, it seems that the situation doesn't change so much, or better, just a little. There we have a little bit of improvement. And then let's check what happens if we increase the derivative value to 120, and it seems that nothing important relevant changed. And let's try with the proportional value and set it at 1000. And let's add again another values in derivatives, and let's put it 150. And it seems as of now, as a first guess, let's say that this free set of value, for the moment, we can keep it as is. So what we can do now is to tune these three values of the joint for position controller, even when we are moving the joint free position controller. So we are tuning two joints at the same time in order to understand and figure it out how they interact between each other due to the inertia values of the link itself that might affect the controller of the joints. So now we can restart all the simulation, and what we can do is to plot in one window the joint position controller, the joint 2 position controller, joint 3 and joint 4 with both the common topic and the state process value topic in such a way that we have a good understanding of how all these joints are interacting, or better interfacing with each other. So let's start from the joint 2 position controller command data and process value. And then make the same for the joint 3 position controller and the joint 4. And after that we have add all these plots. We can start to move every joint and make them oscillate between plus and minus 90 degrees, and see and monitor the behavior of the state process value compared to the command data value for each joint. Okay, we are ready for activating all the joint command data. So we are gonna have a joint 4 position controller, joint 3 and joint 2. Let's start with the moving of the joint 2 position controller, and there is a good overlapping between the command data and the process value. So now let's activate the joint 3 position controller. And you can see from the simulation that the joint 3 is moving to plus 90 degrees, and then switch to minus 90 degrees, and then finally we have activated the joint 4 position controller, and we can see that in particular in the joint 4 position controller there is still a misalignment between the process value and the command data. So, but now if you think we have in just one plot all the behavior of these 3 joints, and we can see now by tuning the PID value of each joint if there is some kind of interference between the tuning of each joint. So something that I see in common between the joint 4 position controller and the joint 3 position controller is that when the angle, the position angle of each joint is approaching the zero angle, there is an offset or a delay, let's say. But when they are approaching the plus or minus 90 degrees, the errors tend to go to zero. So now let's tune the PID values for the joint 3 and joint 4. So let's start with the joint 3, and we still have the proportional, integer and the derivatives of a value of 750 and 100 respectively. Let's try to increase by 1000 the proportional value of joint 3 and see what's happened. Okay, it seems that the error is getting lower even when we are approaching the zero angle, and I'm following with the mouse the light blue and the purple zeta. So I think that adding 1000 with the P, the proportional value, is a good choice. So what you can do is to update right away the proportional value of the joint 3 position controller. And it seems to be stable over the time. So now what we can do is to tune the PID value of the joint 4 position controller, and before we have set the proportional value at 1000, but let's increase to 1700 like we did for the joint 3. And it seems that there is still an error when they are approaching the zero angle. Okay, I'm following with the mouse because it's the green and the brown, light brown curve. So let's increase the proportional value of the joint 4 by 300, so now it's gonna be 2000. And it seems that we have an improvement, but I'm not satisfied yet, so let's increase the integer value a little bit. And I'm still following the error over the time with my mouse. You can follow it as well. It's gonna be the green and the light brown curve, and I think that the error could be negligible. So we can update the proportional and integer value to the values that we have just tuned. Okay, that's all for today. I hope that you enjoyed this video, and if you like this video, don't forget to subscribe to the channel, gives a thumbs up, and turn on the notification bell in order to do not miss the next topic, where we are going to complete our robots. Again, thanks for your attention, and keep learning robotics with ROS. Hi roboticist, we are approaching the end of the modeling of our cobot, 6-axis robot with a gripper as well, and with modeling in URDF and set up all the joint controllers and tuned the PID values for each controllers. So this will be the end of this series of video for how to set up a ROS controller for your custom robot that you have modeled directly from scratch. And before diving into it, make sure to subscribe to the channel if you like this video and turn on the notification bell in order to do not miss the next topic. So now let's start. First of all, we are going to complete our robots, and to do that we need to add the link 5. So you need to go to the URDF file and uncomment for simplicity the transmission tag of the joint that links the link 4 and link 5. Then you need to add the joint 5 position controller, and always keeping the same type of controller that is gonna be, remember you, effort controllers joint position controller. And of course you need to update the joint name that is gonna be link 4 _link 5. Of course you need to uncomment the description of the link 5, this is going to be a cylinder, and the joint as well. And finally you need to update, as always, the arguments of your controller manager node. So now we have everything set up, and we can spawn our robot by launching this launch file in our Gazebo environment. And here we go. You can see that the link 5 is correctly spawned at the edge of the link 4, and it has a position horizontal, and if you press play you can see that all the robot stands. So what we can do now is to check the PID value of our joint 5 position controller. And to do that, as always, we are gonna add to the topic of our RQT GUI the joint 5 position controller command topic, and the type is going to update automatically. Then just set up a little bit better all the windows in order to do not mix up information and see everything that we need in clear mode. So add the frequency at 100 as always. And let's set a command value of 90 degrees, so it's gonna be 1.57, and you can see that the link 5 is moving correctly. Let's try again at minus 90 degrees, see what's happened, and is turning correctly, so he's doing what is supposed to do. So as always, we can plot the joint 5 position controller command slash data topic and make a comparison between the state process value topic of the same joint. So let's add to the plot graphic the command data, and now is set to minus 90 degrees and is stand at that position. And let's check what is the actual value by plotting the state process value topic. Let's add, and you can see that of course are overlapped. But as always, if you want to challenge the good choice of the PID value of your controller, you should send sinus values to your command topic with the amplitude of 90 degrees. So let's do it, and if you press enter, you can see that there's gonna be a step disturb provided by the command data, and in a few milliseconds the real joint position represented by the process value topic reach in a few milliseconds the command data. So meaning that the default PID value are correctly set up. So let's challenge the controller of the joint 5 position controller, and let's increase the velocity of the command data by 3. And you can see that there's always the step disturb, and as always near the 0 position there is very little misalignment between the process value and the data that we are sending. So, and it seems that this error decrease if we decrease the velocity. That's normal, because the more speed you want to send to your joint, is more difficult to the joint, to the hardware itself to follow accordingly. But you can see that for example, if you increase a lot the velocity of this command data, this error increase. So we could set a little bit better the PID control of the joint position controller, and as we did in the last videos, we are going to use the dynamic reconfigure toolbar. So let's looking for the joint 5 position controller. Let's click PID, and here are the values that we have set up for the joint 4 position controller, and we just copy and paste as a first guess in our configuration file. But let's see what's happened if we increase the derivatives value to 200. Okay, the error increase, so this means that it's not a good choice to increase the derivative value in this case. So for the moment, just keep as 150 the derivative values. Or better, let's decrease a little bit. So let's try to increase the velocity and see what's happened, and you can see that the error could be considered as negligible, at least for the joint 5 position controller, with this set of values P, I and D. So we can update the configuration file for the joint 5 position controller. So what we're gonna do now is to make a summary of all the joint position controller that we have tuned before. So it's gonna be joint 5 position controller, a joint 4 position controller, joint 3, joint 2 and joint 1. And for each joint position controller we are gonna plot the command data and the state process value topic in order to have in only one windows all the behavior of all the joint and how all these joint have been tuned. So first let's add all these curve to the matplot. And now joint by joint let's activate the expression for the command data. So the joint 5 position controller is already activated. We have add the joint 2, then joint 3, and you can see that the link are moving accordingly. Then joint 4 position controller, and finally the joint 1 position controller. So all the robot is moving right now, and this robot that we are simulating right now has 5 degrees of freedom, because the 6th we are going to add in a moment, that is going to be the TCP connector. But you can see that all the process value and the data have been well tuned despite the high velocity that we have set up as an expression to the command data for each joint. And this can be considered a good milestone in the ROS controller journey. And I suggest you to take a moment to see how this robot behaves, if the process value follows the command data for a few seconds to see if everything works good and fine. And I think that you can admit that is very satisfying to see all our job that has a completion. So let's close this simulation, and now what we're gonna do is to add the TCP connector and the gripper as well. Here we go. We came back to our URDF file and configuration file, and now what we're gonna do is to add the TCP connector and the gripper as well. So we have uncommented the TCP connector and the joint, and we have add as well the joint 6 position controller that is going to revolute the TCP connector to the link 5. And before to spawn the gripper as well, let's check the behavior in the simulation environment of this last joint. So spawn the robots, and you can see that at the top there is the TCP connector that is put in the horizontal way, and if we press play, we can see that the TCP connector is acting very weird, despite the fact that we didn't send to that joint any command data. The reason is that we have set a PID value that are not appropriate for this particular joint and this link. So, but keep calm and let's be stick to our plan. And we are going to use the same approach as we did in the previous video. So first we're gonna send a value to the command topic that this time we can start as 0. So the command data is receiving a 0 value. Now let's plot the joint 6 position controller command data. Okay, it's 0. But now what's happened if we add the joint 6 position controller state process value? We should see something weird. And in fact the state process value profile has a profile of a saw, let's say, because it's going up and down without any control. So we're going to solve this by tuning the PID value. So let's try, for example, to avoid the derivative value and see what's happened. Apparently nothing happens, even if we delete the integer value. So now let's decrease the proportional value, and you can see that everything is fine now. The process value is overlapping the data value. This is what we should expected. Why that? Well, because the TCP connector, or better, the link that is attached to the link 5 has a less inertia with respect of the other links that are heavier and have a higher inertia. So commonly we can see that is not recommended to put as a first guess a higher value in a proportional control, because otherwise the joint is acting weird, and it seems that we are losing the control of that joint. So let's set 90 degrees with this set of PID values. You can see that after a step disturb, the process value follows very well the command data, and the same behavior you can see that we have obtained for minus 90 degrees. So now we are ready to test the oscillation expression of the command data or the command topic, and we are sending to the command data topic a sinus variable with the amplitude of 90 degrees, and you can see that it follows very good, so meaning that the error is negligible. And let's visualize better by rescale the y-axis in the range that is of interest for us. And okay, there's the same graphics, the two curves are overlapped. So we can make a sensitive analysis. For example, if you put 50 as derivative values, you can see that the saw, let's say, profile of the process value is appearing. This is a good example that proves that in this case, for this link and for this joint, adding a derivatives value decrease the quality of the control. So we can keep a value of 10 for the integer, and now update the PID values for the joint 6 position controller directly to the YOM file. And this is the robot how it looks like. Okay, we are getting closer and closer to the end of this series of ROS Control. What is missing now is to spawn the grippers and tune those joints that this time are not revolute joint but will be a prismatic joint. So the edge of the gripper is sliding on a surface of the TCP connector. And here we go. Now what we need to do is to uncomment the gripper right link and the TCP connector gripper right joint, and the same things for the gripper left and its joint. And then we need to uncomment the transmission tag for the joint that links the grippers left and right to the TCP connector. And then we need to add or better update the configuration file by adding the gripper right position controller. We can call it like this. Of course, we need to update the joint name, that is going to be TCP connector _ gripper right. So for the moment, just keep as always the same convention of naming every joint and every position controller. So then copy and paste for the grip left position controller, and for the moment just keep the PID value as is. We are going to tune later on in this video. And then for last, we can finish our launch file by updating the arguments of our controller manager nodes. So add the gripper right position controller as well as the gripper left position controller. Okay, we have finished and we have everything set up to test this final robot in our Gazebo simulation. So ROS launch, name of this launch file, and here we go. We have correctly spawned all our robots that we have previously designed in our URDF file. We have tuned all the joint with the exception of the grippers right and left. So if we press play, let's see what's happened, and you can see that the gripper right is not going to the right position, and everything is it seems to falling down, but it's not falling due to the controller setup of the previous joint. Okay, so we can continue our approach, and so we can send to the grip right position controller a value or better an expression of 0, and you can see that the gripper right link is acting weird, and we have seen before with the TCP controller. This means that the PID values are not correctly tuned for that kind of joint and that kind of link. So if we wanted to figure it out how far we are from a good tuning, let's plot the gripper right position controller command data and the gripper right position controller status process value. And let's see what's going on. Okay, you can see now that the state process values has a wave behavior, even if the command data is set as an expression of a set point, 0 position. But besides that, the state process value of the gripper right position controller has a misalignment, or better, has an offset of round about 0.03, and another problem is that is acting as a wave, and this is something that we don't want to happen. So let's try to see how the changement of the PID value affect the state process value control. So if we increase a little bit the proportional value, well, the effect of the wave is increasing, so it's not considered a good choice. So I would increase a lot, but what happens if we increase a lot? Well, it seems that we still have a wave profile, but this time the state process value is getting closer to the common data value. So meaning that it could be considered a good choice to increase a lot the proportional value of our PID controller of the gripper right position controller. So let's try to make a set point of 0.05, and the process value follows correctly the command data. As you can see, if we go from 0 to 0.05, which I remember you are the lower and the upper limit respectively of your gripper right, and yeah, you can see that it seems that with this set of PID value the grippers act correctly. So we have it seems that we have found our PID value, and let's update it directly to the YUM file. And of course, since that the gripper left is going to be the same in dimension at least as the gripper right, we know already somehow the PID value that we need to put for the gripper left position controller. But anyway, let's plot right now. So let's plot the gripper left state process value and the command data. And it should act as before, because it's register wrong PID values. So in fact, if we press OK, now I remember you that this time the limits are between minus 0.05 and 0. And let's see what happened, and you can see that there is still this wave behavior, and with an offset of around about 0.3. So we can do the same as we did for the gripper right position controller, and let's put the same value that we found for the gripper right. You can see that if we increase the proportional value, there is still this wave effect that is going to be cancelled with the adding of the integer value. It's not enough a huge value of this, but 10 it will be enough, as you can see. And then you can challenge your PID control. For example, if for both grippers we set 0, 0, the gripper is totally opened, and if for example for the gripper right we set an expression of 0.05 and minus 0.05 for the gripper left, the gripper should close. Let's check it. And you can see that it's closed, and the both state process value of the gripper right and the gripper left follows correctly without introducing any error the command data. So it seems that we have everything set up. We have spawned completely our 6-axis robot with the gripper as well. Slider grippers for the moment is a good example, and we have tuned all the 6 joints plus 2 joints, prismatic joint for the grippers. And we can consider that it is a really good achievement, and basically we are at the end of our journey. So since that we have everything set up, feel free to play with your robot, sending a sinus expression to each joint and see how it behaves. And it's very important to see how the robot overall behaves by sending a different kind of command data topic. You can use an expression, you can use a scalar value. So let's try a little bit and make the windows in such a way that we can see the robot acting. Let's set an oscillation expression for the joint 4 position controller. As well for the joint 5 position controller, and we can keep the expression that we have set up in the last video. And for the joint 6 position controller we can set up at 0, and if we activate everything we can see how the whole robot acts. Every joint here is oscillating between minus 90 degrees and plus 90 degrees, which I think it's very nice to see the result of our work. Okay, now let's put to each joint a scalar expression. Let's set at 0 for each joint and see what happens, and it should go into the default position that we have set in our URDF file. So we have start with the joint 2, then move the joint 1. Okay, then we are gonna send to the 0 position the joint 3. Here you go. Then do the same for the joint 4. You see what's happening? The robot is going to the 0 position, so the joint 5 is going to reach the 0 position, and the joint 6 was already at that position. And here we go. From an oscillation behavior of each joint, we goes to a default position of 0 degrees for each joint. So meaning that this robot acts as we want. So let's make another thing, and let's set for each joint 90 degrees of angles, and to see at what position the TCP is going to go. So for example, we are going to set 90 degrees for joint 1, 1 radians for joint 2, 90 degrees for joint 3, joint 4, joint 5, and for joint 6 let's put a value of 2 in radians. Okay, so let's tip the windows, and the robot is going to the position that we have asked him to go. And this is an example of a forward kinematics where we have set up the joint position of each joint, and the TCP goes accordingly. So before to close, let's remember to update the YUM file for the gripper left position controller, and now let's test it again. Let's do another foor kinematics exercise by setting to all of joints a 0 command, and the robots will go to the standard position. Here we go. Joint 1, joint 2, joint 3, joint 4 is standing completely, and all the joints are correctly tuned, and everything is working properly and smoothly. So I hope that now you got the point, and feel free to try no matter expression that you want to ask your robot to do. So just put some random value for each joint and see for the last time how it behaves. And here you go. And then in direct we can see how each joint goes and the behaviors of each joint that is going to the setup command position. So, congratulations, that's all for today and for this ROS Control series. I hope that you enjoyed this ROS Control series and that you got a lot of technical value out from this. And if we want to make a recap, we can summarize in this PowerPoint presentation, where we have set up all the transmission tag for our joint. We have created the configuration file. We have set up the launch file to spawn not only the URDF file of our robots, but also each controllers that has been configured in the YUM file. And finally, you have learned how to tune the PID values of each controller. You have seen how the proportional, integer and derivative values affect the alignment between the status process value and the command data value of each joint. And with all this in mind, you have reached a good milestone that allows you to model your own robots and to control it using the ROS Control package, or better, the controller manager node of ROS. If you like this video, don't forget to subscribe to the channel and turn on the notification bell. And if you want to have more topic, and if you want me to go deeper in ROS Control, because there's something that you didn't understand, just write me in the comment down below, and I will reach you out as soon as possible. Another important thing is that in the description section of this video, I have put my GitHub repository, where you can find all the model, all the cobot simulation package, let's say. So feel free to have a look on that, check it out, download, and try to implement your robot with your ROS control. So, thank you for your attention, and keep learning robotics with ROS.